Hello, this is Dr. Viv. I would like to discuss today an important topic called the center of mass of a system. To begin with, we'll consider a discrete system, and a few videos later I will get into continuous systems of masses. Discrete means each mass can be considered a point. Now when I say it can be considered a point, I mean it doesn't need to be a point. For example, this could be a sphere with its center of gravity in the middle. And so if you have a regular object with a known location of a effective place where you can concentrate all the mass, then that's also considered point mass by this definition of mine. Well, the center of mass is a simple mathematical definition and resembles what you might call the weighted average. So the definition of center of mass is the following. The coordinate r measures the effective location of all these masses. So each one is got some vector that describes its position from some origin O. And the center of mass is like the weighted average weighted by the masses. So it's going to be the sum from I equal to 1 up to n, m sub I, r sub I, divided by the sum of all the masses. Where in general r equals xi hat plus yj hat plus zk hat, the position vector. Now because of that, I can write three separate equations for the x, y, and z center of mass. So the x center of mass is going to be sigma mi xi. I'll omit the I equals 1 to n. Y center of mass is the sigma mi yi over the sum of all the masses, or the total mass. And the z center of mass is sum mi zi over the total mass. These three definitions are easier to work with than the vector definition. There is another notation for center of mass, and that is, this is sometimes written as x bar, that is sometimes written as y bar, and that is sometimes written as z bar. I will be using either one interchangeably. Let's take our first example of center of mass. So suppose I have an object that is a uneven object. Well, I can try to approximate the uneven object with two masses. So think of something like this. Here's a little train here. Now you generally know how to find the center of mass from tricks that you may have learned as children. You take these two fingers together, and then where the fingers coincide is pretty much going to be right under the center of mass. So the center of mass of this locomotive is over here. And if I want to hang this on a Christmas ornament, I'd put string around this point and it'll be level. So these are the obvious things that you know already from just being around on the planet. So let's figure out how to model that locomotive I just showed you. So I'm going to just say that I have a particle of mass, let's say 3m here, and a particle of mass 2m over here. So that's the front end of the locomotive, which is more massive, and that's the back end, which is less massive, connected by a light rigid rod of length L. So you can find out where the center of mass is. A good way to do this calculation is to assume that it's somewhere over here, call it the origin O, then call that distance x1 and call this distance x2. We'll use the x definition of the center of mass because this is along the x-axis. Let us calculate. I'm going to get 3m times x1 plus m times 2m times x2 divided by the total mass, which is going to be 5m. That's going to be 0 because I've chosen the origin to be the center of mass. Let's work this out. Well, all the m's cancel out, so I'm going to get x1 equals negative 2/3 x2. Now I also know that the length of the train is just the absolute value of x1 and x2. I take absolute value because I'm not too interested in the fact that x1 is negative, and that's going to be L. So let's calculate this. x1 is 2/3 x2 plus x2 equals L. 2/3 plus 1 is 5/3. And that tells me that x2 is 3/5 L, and because x2 is 3/5 L, that means x1 must be 2/5 L. So it's exactly what you expect. The center of gravity is 40% over here and 60% over there. So that's how you would use the center of mass in making such simple calculations. Let's try a two-dimensional example next. I have the y-axis and the x-axis, and let's suppose I keep a mass here. Let's suppose I keep 3 coins, like 3 quarters, 25-cent coins, and here I keep 5 quarters. If the mass is bigger, I'll start drawing bigger circles. And here I keep 2 quarters. So this distance, I'll say, is 3 units. How about centimeters? And this distance is 4 centimeters. So 1, 2, 3, 1, 2, 3, 4. Let's find out where the center of mass is. I mean, you know it's going to be somewhere there, but exactly where? This time we have both x and y, so we have to use this formula for the x and that formula for the y. So x bar is going to be 5 times 0, because the x coordinate for 5 is 0, plus 3 times 0, plus 2 times 4. Only 2 has a non-vanishing x coordinate, and then the total mass is that 5 plus 3 plus 2. Well, that's 8 over 10, which is 0.8 centimeters. Let's calculate y bar. That's 5 times 3, and the remaining 2 have 0 y coordinates over the same total mass of 10. So that's 15 over 10, which is 1.5 centimeters. So the center of mass is going to be x 0.8, y 1.5. So that's a precise location of the center of mass. I like to indicate the center of mass with a dot with a circle around it. Third example. Let's try something interesting. How about a disk with a hole in it? So you may wonder, is he going to do calculus? Well, even though I could, you don't really have to. This is more common sense than anything technical. So let's just draw a circle of radius r. Apologize in advance to my circles. I'm not treating them well today, but that's what it is. So I've created a metallic sculpture by stamping out another circle. So when I put this shading, I mean that that's the material that's there, and the hole has been stamped out. You know that the center of mass has to be somewhere here, probably somewhere over there, okay, because that's got more material than this side, but exactly where is it? The radius of the circle is, let's say, r. So what we're going to do is something that would probably occur to most of you if you stare at this long enough. We're going to say that a object with a hole is equal to an intact object of mass m plus another intact object with negative mass. So it's as though the hole is made of another material with antimatter, and then when it comes in contact with matter, it just poof, evaporates in a big flash of light. We're going to use that basic concept. The other thing that will be useful for us is to define a quantity known as mass density. The units of mass density are kg per square meter. This is more like the surface mass density. It's not the usual meaning of density, which is mass divided by volume. This is a surface mass density, hence it's kg per meter squared. This will allow us to convert areas to masses. So the mass of the intact object in this case is sigma times pi r squared, because that's the area of the circle. The negative mass will be sigma times pi r over 2 squared, because that's the radius of the hole. And so when you do 1/2 squared, you're going to get negative quarter sigma pi r squared. And now we already know that the y-coordinate center of mass is 0 by symmetry, so all we have to do is calculate the x-coordinate center of mass. So x bar, by the definition of center of gravity written here, sigma mi xi divided by sigma mi. Because I've chosen the origin to be exactly where the positive mass is, it's going to be capital M times 0 plus the negative mass, I call it m prime for some reason, I could have just called it m, times r over 2, because that's where the negative mass's center of mass is located, divided by m plus m prime. Now it's just a matter of substituting values. So for m prime I'll get that, negative 1/4 sigma pi r squared times r over 2, and in the denominator I have sigma times pi r squared for capital M, and negative 1/4 sigma pi r squared for m prime. The first thing you immediately notice is that sigmas cancel out, so it really doesn't matter of what material this is made. Pi's also cancel out. So I'm going to get 4 times 2, 8. This is going to be a negative 1/8 r cubed up here, and then I'll have r squared minus quarter r squared, which is 3/4 r squared. Cancelling out, I get r, which makes excellent sense because center of mass has to be a distance or length. And 4 goes 2 times into 8. That gives me negative r over 6. As a simple example, I urge you to consider the following problem. Rotate this around the x-axis. Then you're going to get a bowling ball with a hole in it. Think of it as a bowling ball with a laser cut hole in it. Maybe someone's trying to gain an advantage in a bowling competition, and they figure that if they laser cut a hole, then it will go better and avoid the gutter or something like that. So you're in a process of checking the center of mass of a bowling ball, and you want to make sure nobody is cheating like this. So before the competition, what you do is you calculate what it would be. So rotate this around and make it a three-dimensional problem. You have to use the exact same ideas, except you have to use the volume of a sphere instead of area of a circle. I invite you to try that. You can put your answers on the chat if you like.